All right, in this video, we're going to look at rational power and root functions. So if we have a function where we've got x to some exponent, where b is a constant, just some number, that's called a power function. All right, and so if b is a fraction where it's not just a denominator of 1, so like where the denominator n is greater than or equal to 2, so for example, like this would be then f of x is equal to x to the 1/2, something like that, then it's called a root function, and we can rewrite that as a radical. So if it's a square root, we would write it like that. We could have another function where we might have like x to the 1/3, and that can be written as a cube root. So now if we have if our denominator is odd, like in this case, it's an odd denominator, an odd kind of a root, then the domain is all reals. But if we have a function whose denominator is even, like this, in this case, it's a square root. Another example would be like a 4th root, 6th root, anything even. So if the denominator is even, then we need to have the domain is limited to just only all positive real numbers. All right, so when we graph power functions, so I am looking at f of x is equal to x to the b, where b is 0.3, 1, or 1.7, and where x is just positive or real numbers, or it could also be 0. So what happens is our exponent has an impact on how steeply our graph increases. These are all increasing graphs. But as b, the larger value of b causes the graph of f of x to increase faster. So the larger this is, f of x is equal to x to the 1.7. And this one is just that f of x equals x to the 1. That's just a line, y equals x. And then this one is f of x equals x to the 3/10, 0.3. Okay, so the big thing to remember is the exponent. If it's greater than 1, then we're going to have a very steeply rising curve, and if it's equal to 1, then that's just the same as that line y equals x, because x is the same thing as x to the 1. Now if we have our exponent between 0 and 1, then it's just going to be this root function, which is kind of a nice shallow, it looks like a little not very steep hill. All right, so we're going to just apply properties of rational exponents, so there should be a little bit of review. The numerator is telling us the power, and the denominator is telling us the kind of root that we have. Okay, so I can rewrite that. It's going to be a 4th root of 16, and that's all being taken to the 3rd power. All right, now the 4th root of 16 is saying what times what time, something times itself 4 times. And let's see, 2 times 2 is 4, times another 2 times 2, that is 16. So 2 to the 4th is 16. And that means that the 4th root of 16 is 2. And then we're taking and cubing that. 2 cubed is 8. All right, let's try this next one. The cube root of negative 64. I'm thinking it's probably negative maybe 4. Let's see, negative 4 times negative 4 times negative 4. Negative times negative is positive, so that would be positive 16 times negative 4, which would be negative 64. Okay, so because negative 4 cubed is equal to negative 64, that means that the cube root of negative 64 is negative 4. And then when we take that to the 4th power, I have to figure this out. All right, it would be a positive 256, because negative 4 times itself 4 times, that would be end up being 16, positive 16 times positive 16, which is 256. All right, let's try one more. So our 2 is the power, And our 3 is telling us the kind of root. Okay, so this simplifies as a cube root of negative 125 all to the second power. The cube root of 125 is negative 5. And then when we square that, we would get a positive 25. All right, now let's rewrite radicals with rational exponents. So if this we don't write it with a 2, but that is a square root. This is the same thing as x to the 1/2. All right, so that 2 just isn't written, although it is assumed that it's there. Okay, so the denominator is telling me the kind of root, and the numerator is telling me the kind of power. So cube root of x squared is the same as x to the 2/3. Denominator is telling me the kind of root. Okay, and that power of negative 5 is my numerator. And then this I can simplify, because if I have a negative exponent, then that would mean that it's the reciprocal. So 1 over z to the 5/4 power. 1 to any power is still just 1, and then it would be z to the 5/4 power. So 1 over z to the 5/4. Okay, and last one. Okay, I have a square root. So all of this is being taken to the 1/2. And then inside here I have y to the 1, or to the cube root. So I'm going to write that as y to the 1/3. And then I have the 4th root of y, which I'm going to rewrite as y to the 1/4. Now I'm going to use my exponent rules. When I'm multiplying with the same base, I get to add exponents. And that's still all being taken to the 1/2 power. Okay, getting common denominator. I'd multiply my first fraction by 4 over 4, my second fraction by 3 over 3, and I get y to the 4/3 plus, not 4/3, 4/12 plus 3/12, and that's all still being taken to the 1/2. So this would give me y to the 7/12 to the 1/2. And now I'm going to use my power rule of exponents. I'm going to multiply those. So this would be y to the 7/12 times 1/2, which gives me a grand total of y to the 7 over 24. And that's done. All right, now we're going to be looking at graphing and looking at transformations of power and root functions. So if we have a power function that has an even index, so this number, that's the index, and if that's even, then, let's see, if that's even, then our domain is limited to all positive real numbers, including 0. So we're going to have a bracket because it can include that 0. Okay, and then the range is all positive numbers as well. Okay, now if it's an odd index, then our domain and range are unlimited. It's all real numbers. Okay, so let's find the domain. For this function, because it's an even, there's no 2, but it's assumed that that is a 2. If there's no index, it is a 2. Okay, so it's an even kind of a root, and that means that my domain is limited, that whatever I'm taking the square root of needs to be either equal to 0 or greater than 0. Okay, so the process here to find the domain is we set the radicand greater than or equal to 0. And then we'll just solve that. So I'll just subtract 12 from both sides, and that would give me 4x is greater than or equal to negative 12. And just solving through, I'm going to divide by 4. So I've got that x is greater than or equal to negative 3. And then I can look at that in terms of a interval. I'd be at negative 3. That's going to be because of this equals. I'm including that and heading off towards infinity. So my interval would be bracket because of the equals from 3 to infinity. Okay, and there's our domain. Okay, let's try one more. Here we've got a function with an odd index, and so that means that my domain can be all reals. All right, let's look and see how we can use transformations to find the graph and also be able to visually see what that domain and range is. So if we're looking at this function y equals the square root of 4x plus 12. So in terms of transformations of the parent graph y equals square root of x, if I simplify that radicand a little bit, I'm gonna factor out my 4, and then I can take the square root of 4 separately, and so square root of 4 is 2 times the square root of x plus 3. So that coefficient of 2, what that means is I'm going to that's going to stretch my graph vertically by a factor of 2. So all the outputs would just increase. Everything's going to get multiplied by 2. All right, now that minus 3, or that plus 3 here is going to shift my graph back by 3 units. Okay, so I'll have shifted left 3 units. So you can kind of look at my original parent function. I just square root my numbers. Go square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. And so there would be my original parent graph. And then all of the outputs going to get multiplied by 2. So 0 times 2 is still 0. 0 times 1 is, 1 times 2 is 2, so that increased, and this one increased up to 4. So it's rising more quickly, but it also is shifting left 3 units. So the domain is x minus 3, which we got before, and now my range, it hasn't been reflected across the x-axis, it hasn't been shifted vertically, and so my range is still the same as the parent graph of y equals square root of x. It's still 0 to infinity. All right, let's try this next one. So we have y equals the cube root of negative 8 x plus 8. So I'm going to simplify that radicand a little bit. If I factor out a negative 8, I would get x minus 1. Right, it's like undoing this, the distributing. Negative 8 times x, that's negative 8x. Negative 8 times negative 1 is a plus 8. Okay, then I can take the cube root of negative 8 and the cube root of x minus 1. That's negative. The cube root of negative 8 is negative 2. And then the cube root of x minus 1. So here we have a coefficient of negative 2. So the negative means that it's going to be reflected across the x-axis. And the 2 there means that we're going to have a steeper, now they're going below the x-axis, so but it's still a vertical stretch. It's now that they're going downward, so it's still a vertical stretch by a factor of 2. Okay, and then that minus 3 moves that we will, or the minus 1 means that we will shift, we're going to shift right by 1 unit. Okay, so now I can come up with the graph. Okay, the original y equals cube root of x. We could have, let's say, negative 8, negative 1, 0, 1, 8. We'll just do some points here. Cube root of negative 8 is negative 2. Cube root of negative 1 is -1, 0, 1, and 2. Okay, and so that the domain, because it's an odd index, it's an odd root, the domain is unlimited. It's going from -infinity to infinity, as is the range, because I can take the cube root of a negative number and my output I can take, that's fine, that's real. Okay, so my domain and range are all reals, but here if x is -8, my y would be -2. And at -1, I'm here, and at 0. So it's just not a very steep curve. Okay, so what my curve now is going to do is I need to reflect across the x-axis, so I'm going to be here. So this point that was at 1, 1 is now going to be at 1, -1. Okay, this point here reflects across, so at -1, it's at +1. This point right here was at -8, -2, and that's now at +2. So my curve is going to go like that because of the reflection. There's going to be another point here that was at -8, -2. Or +8, sorry, +8, -2. So that's the reflection, but now we have it stretching. Okay, so this stretching means that I need to multiply my output by 2. So my new point is going to be twice as high. So it'll be at -8 and now 4. This would be, didn't affect the x, but my y value gets multiplied by 2. So it's going to be up here. Okay, we're going to have a point at 1 and -2. The y values are getting doubled. 1, 2, 3. Oh, that point wasn't quite right. Let me fix that. That point should have been at 2. Okay, and then this point is at -4. This point is at 8. My x value doesn't change, but now my y value is doubled. Okay, so there's this one is a little bit too high. Let's see, this guy just reflected, so we're at 1. Okay, and now this guy just doubled, so he would have been here at 2. All right, and now my shift right, it's just going to move my x value. So if there's a change to the input, then it's affecting the x coordinates. Okay, so now everything is just that whole blue graph right in here. This whole thing is just going to shift over to the right by 1 unit. Okay, so let's get our final graph. Okay, so this point -8, 4. Now we're going to be at -7, 4. Okay, we had a point at -1, 2. Now we're going to be at 0, 2. We had a point at 0, 0. Now we're going to be at 1, 0. Okay, and then we had a point at 1, -2. Now we're going to be at 2, -2. Okay, and our final point, 8, -4. Now we're going to be at 9, -4. All right, and so now we can finally do that shift to get our final graph. Okay, so that curve has just slid over to the right by 1 unit. All right, so we can do it like that with the transformations. The other thing that you can do is just, just make an XY table for yourself with our new function. So it would be -2 times the cube root of x minus 1. Okay, and originally we had these points at -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. Okay, and so subtracting 1, that's going to affect our x, and that's going to shift our graph to the right. So instead of a point at -8, we'll be at -7. Everything's just getting added. One is being added to the x value of each of those original points. So now we're at 1, 2, and 9. And it can be a little bit confusing keeping track of all of the stretching and shifting vertically that we're doing. So what we can do instead is just go ahead and work this out. So we'd have -2 times the cube root of -7 minus 1. So that'd be -2 times the cube root of -8. And since the cube root of -8 is -2, we'd get -2 times -2, which is 4. Okay, and so that has two things happening to the -2. It's reflected, which makes it positive, and it has a vertical shift by a factor of 2, so it's also doubled. Okay, so let's try this, see if we can come up with it. So reflection would make it +1, and doubled would make it +2. Okay, but we can also just work that out. Cube root of x, in this case x is 0, minus 1. So it would be -2 times the cube root of -1, which is the -2 times cube root of -1 is -1. -2 times -1 is a +2. Okay, so let's try this one. Our input is 1. So we're going to go do -2 times the cube root of 1 minus 1. But we can try, just thinking of transformations. So 0 reflected is still 0. 0 doubled is still 0. Okay, let's see the algebra here. Cube root of 1 minus 1 is 0. And then we're doubling it and making it negative, right? Doubling it because of the vertical shift, making it negative because of the reflection across the x-axis. Cube root of 0 is still 0, so my output is 0. Okay, let's try this one. Our input is 2. Okay, my x is 1. When I reflect it, I get -1. And when I double that, I get -2. And the algebra here would be cube root of 2 minus 1 would be the same as cube root of 1. So it would be -2 times cube root of 1 is just 1. Okay, good. All right, and finally 9. We have the cube root of 9 minus 1. Okay, doubling it, we would get 4. Making that negative, it's -4. Okay, so -2 times cube root of 9 minus 1 is 8. So it would be -2 times the cube root of 8 is +2. We're doubling it because of the vertical shift, and we're making it negative because of the reflection across the x-axis. Okay, so there's the other way of doing it, and then you would just plot those points. And there we have it. There's our graph, and our domain and range are both +∞ to -∞. All right, let's do one more example. Use transformations to explain how the graph of the given function can be obtained from the graph of y equals square root of x. Okay, so here's our strategy. As we do the algebra, simplify the algebra here. If I factor out a 9, I would get x plus 3. And then plus 3. Okay, then I'm going to take the square root of 9 separately. Square root of x plus 3 plus 3. So square root of 9 is 3. Then I would have that be multiplied times x plus 3 plus 3. Okay, coefficient. That gives, if it's a number greater than 1, it's a vertical stretch. If it's a number that's a fraction smaller than 1, it would be shrinking it. Okay, now if I have something impacting and going in and affecting my x, that means it's a movement along the x-axis, so it's moving horizontally. If I add a number, okay, then that would be a shift to the left. Okay, and then finally I have this +3, and that is adding something at the end. I think of that like adding on to the output. And so what that does is it is a vertical shift up 3 units.